Hantzsch dihydropyridine synthesis is a multi-component organic reaction between an aldehyde, two equivalents of a beta-keto ester, and a primary amine. The initial reaction product is a dihydropyridine, which can be oxidized in a subsequent step to a pyridine. This reaction was reported in 1881 by Arthur Rudolph Hantzsch. Hantzsch esters are an important class of calcium channel blockers and is commercialized in, for instance, nifedipine, amlodipine, or nimodipine. The reaction has been demonstrated to proceed in water as reaction solvent and with direct aromatization by ferric chloride, manganese dioxide, or potassium permanganate in a one-pot synthesis. In order to form Hantzsch ester or dihydropyridine, there are three components to this Hantzsch dihydropyridine synthesis: an aldehyde, two equivalents of beta-keto ester, and either primary amine or ammonia. So let's understand the mechanism. So there are two components to this mechanism. First is generating an alpha-beta keto ester using basic condition and enamine using acidic condition. So let's generate this alpha-beta keto ester first. So a base is going to come, it's going to abstract that acidic proton, forming this enolate. So it's going to push that electron density towards that oxygen, right? You form this enolate. So once enolate is formed, it's going to act as a nucleophile. And you have an electrophile right here, which is an aldehyde. So now you're going to generate this. That oxygen is negatively charged, so it's just going to abstract hydrogen. Once that's done, a base is going to come again, and it's going to form the enolate. So this acidic proton, right, is going to be abstracted by that base. After that, now you have a good leaving group, a hydroxide, since this is a basic condition. So that negative charge on that oxygen, right, that means it's electron rich, is going to drive that electron density and now forming this alpha-beta keto ester. Now, how do you form an enamine? So you use acidic condition. So this ketone, right, is going to act as a nucleophile, abstract that proton, become protonated, then a primary amine is going to come, and we're going to have a nucleophilic attack on this electrophilic site, which is the carbon. After that, you're going to get a protonated amine. So proton transfer is going to happen, and now we generated a good leaving group, which is water. So this nitrogen, the lone pair on it, is going to come down, expel that water out, forming this iminium ion. But remember, we have this acidic proton, so base is going to come and form this enamine. After enamine is formed and you have this alpha-beta keto ester, we're going to get 1,4-Michael addition. Since this enamine is a soft nucleophile, the lone pair on it is going to come down, and we're going to get that pi bond nucleophilic attack here, and this pi bond is going to break, generating enolate. So we have an enolate and a iminium ion. So a protonated nitrogen and negatively charged oxygen. So we're going to get a proton transfer. I forgot to mention that this ester group, for ease, we're just going to label it as R5. So it's easier to work with. So once proton transfer happens, this enol, right, is going to come down and abstract that hydrogen. After that, it's going to become protonated. Now this is where stuff gets interesting. So base is going to come, right? It's going to grab that acidic proton. It's going to drive that arrow here, form a double bond, and you're going to get that imine attack on this electrophilic site, which is your carbonyl, so this carbon, and it's going to push the electron density towards that hydroxyl group. So you're going to get a ring closure. After that, the hydroxyl group is going to get protonated. So now you have a good leaving group, which is water. A base is going to come, abstract that proton, and now you're going to generate that pi bond, and that water is going to be expelled. So now you're going to get this dihydropyridine. So that's all for Hantzsch dihydropyridine synthesis.